little quick aside, really, to talk about gravity inside the Earth. So talk about where that comes from, and mostly just a little quick chance to relate this to a bit of simple harmonic motion and just revise a bit of simple harmonic motion. So if we were to look inside the Earth, alright, gravity would be different. So if you use your distance from the centre of the Earth to calculate gravity here, it's okay. You can imagine that all of the mass of the Earth is concentrated at one point at the same distance away as the centre of the Earth is. Obviously that's not actually what the Earth's like. Some of the Earth's quite close to you. So a small amount of the Earth's very close to you and has a big effect, but quite a lot of the mass of the Earth is further away than the centre of the Earth. It just so happens that the maths works out that those effects cancel each other out, and we can pretend that all the mass is at the centre. So we can take this a little bit further with something called Gauss's theorem. Okay, this is not on the spec, so don't get too worried about it. Just interesting to have a look at. So when we're on the outside of the Earth here, we can pretend that all of the mass of the Earth is here. But when we go inside the Earth, this ceases to be the case, because this mass here that's further away from the centre than us and behind us is pulling backwards, and this piece of mass here, which is also further from the centre of the Earth than us but on the other side, is pulling the opposite way. Now if you do some slightly tricky algebra and a little bit of calculus, which is more than we want to do here, but it was just about within A-level maths, you can prove that these two actually cancel each other out. So this large mass over here quite a long way away and this smaller mass here close to you actually have the same effect. So what you've got is the same effect as if you had a planet this big and all of that mass was pulling you towards the centre. So we can look at that, and we know the strength of gravity is gm over r squared. So we know that the relevant mass here is no longer the entire mass of the Earth. This is now the volume that's closer to the centre than us times the density. So that's 4/3 pi r cubed for the volume times rho for the density. Okay, this does assume that the density of the Earth is uniform, which certainly isn't the case, but it's not too bad an approximation. So that simplifies to g equals 4/3 g pi r. So you'll notice the r cubed cancels out with the r squared. It just leaves us r rho. And what that's telling us is that the strength of the gravitational field is proportional to the distance from the centre. Okay, so if we plot this out on the graph, we already know the part over here. This is our 1 over r squared graph, but inside the Earth is proportional. So at the centre of the Earth, as you might be able to work out, if we were right in the middle, we've got gravity pulling in all directions equally. So that cancels out, so the total gravitational effect is 0. But it gets more and more, but it goes up in a linear way. Okay, so we can apply that if you want to look at real physics. They've got an example of this from the movies. Okay, but we're just going to look at the physics of it here. So the acceleration is proportional to displacement, which is our definition for simple harmonic motion. If you remember, the key thing for simple harmonic motion was A is proportional to minus kx. So that gives us our maximum acceleration, which is the one we already know, is minus 2 pi f squared times A, the amplitude, which in this case is going to be the radius of the Earth. So 9.8, the gravity at the surface of the Earth, is 2 pi f squared times the radius of the Earth. This is going to tell us if we drop something down this hole that goes straight through the middle of the Earth, how long will it take, or what will its frequency be in the first place, as it oscillates under simple harmonic motion going through the Earth. Okay, so we just square out the brackets and rearrange it. We get that frequency as 1.97 times 10 to the minus 4 hertz. The period is 1 over the frequency, so that's about 5,000 seconds. So if you dug a hole right through to the centre of the Earth to the side and you drop something down it, it would accelerate. The maximum acceleration would be when it left your hand. The maximum velocity would be as it passed through the middle of the Earth, but the time it would take to go all the way down and all the way back to you again would be just over 5,000 seconds. Okay, if you just wanted to send a message to the other side of the Earth, it would take you half of that time, 2,500 seconds.